Okay, our next speaker is going to be Mark Smith. I think he's having a little, there he is.
Hi. All right, can everybody hear me okay? And I'm going to share my screen really quick. Share. Oops. Let's go back to the beginning. Okay, can everyone see slide 1? Okay. All right, perfect. Thank you, Lauren. Okay, before I begin, I want to thank everybody in the attendance for coming. I actually see a lot of familiar names, which is really terrific. It's great to have you. I'd also really like to thank Austin Mass and Genevieve Rios for including me, as well as my fellow presenters. Yeah, I feel pretty privileged to be among this audience and present this here today. That was a great talk by Duncan. It was great to see the significance behind 3D models, why people are creating 3D models. Let me see if I can move that. There we go. And now my talk is going to be a little bit more technical. It's going to describe a lot of the methods in image capture and walk you through how a 3D model is made. Ideally, this talk would be closer to about 45 minutes to an hour, so I apologize if I have to skip over a lot of details, but I'm going to give you some resources to basically show you where to go when you need to find more information. So my talk today is titled A Tutorial on Creating 3D Models Using Methods in Focus Stacking and Photogrammetry. And the way that this is structured is mainly going to be around this single specimen. So this specimen is going to be Halictus tripartitus. It's a relatively small bee. You can tell by the scale here. It's somewhat iridescent, and it's also hairy. So it has a lot of technical characteristics that make it kind of challenging to 3D model. So I'm going to give you a full workflow which it combines the methods in focus stacking as well as 3D rotation in order to build this model. And if there's time at the end, I'm also going to present 3 shorter versions of a few different specimens that we can also 3D model. One is actually a dolphin neck vertebra. This was a specimen provided by my wife, who is a PhD in biology at University of St. Joseph in West Hartford. She wanted this as a teaching instrument to show why marine mammals have a very compressed neck vertebra. This is a larger specimen. It's about 25 centimeters long, so very, very different from the bee. And you can see the capture time is only 10 to 25 minutes, whereas the prior was closer to 90 minutes, and we'll get to that. This one here is going to be a drill core specimen. So again, this is several centimeters long, probably about 35 centimeters long, but this is a panoramic, focus stacked, and rotated image. So we have 5 axes of motion here. So I want to quickly showcase how a model like this would be created. And then I want to present something that's very, very technical. So this is these are roots that were grown in plastic cuvettes inside of a clear agar. So we had many, many issues to sort through in order to build an accurate 3D model, but I'm going to present some information about this as well. So to get started, I'm going to talk about the tools that we use in order to use this. At Macroscopic Solutions, we sell several off-the-shelf systems. Among them, and our most popular, is called the Macropod Pro 3D. There's actually several people here that I believe have this system. And what we try to do is build a system with professional imaging components with one camera where the sample is being rotated and manipulated to capture different changes in perspective or different focal planes. We include several different lenses to accommodate different sizes, and then several different techniques and lighting configurations to illuminate those specimens. We're not always after the prettiest image. Most of the time, we're after scientific rich images. So images that, they don't contain glare, they're more matte looking. We're trying to visualize data and information that we can then measure or quantify. So I know that I have to talk through every slide. I put this here because I figured people could screenshot it really quick if they're curious about what's in the system. I'm going to really quickly try and go over this. I apologize if I don't read every component. But in that system, I just wanted to list a few of the main core components that are included. We include the Canon EOS R5, the Canon RF 70-200, 24-105, 100 millimeter, as well as several scientific optics ranging from 2x to 100x. And those are the Mitutoyo M-Plan APOs. Our lighting system is a wireless Godox flash system. We include 4 flash heads. 2 remain on a charger while the other 2 are in use. We have part of our automated systems, which is done by Cognisys. We have the stack shot controller, and then we have a rotary stage by them as well. And then we have the hardware platform, which is now completely built and designed by me at Macroscopic Solutions. And we have several accessories that are more accommodating of several specimens. And then the software, we have Agisoft Metashape, which is the primary 3D modeling software, which Macroscopic Solutions is the US distributor for. And then Zerane Stacker, which is our focus stacking software written by Rick Littlefield, who I'm actually very happy to report is attending this talk today. So I want to talk a little bit about the computing requirements, because for Metashape to work, it requires a pretty powerful computer. Key takeaways, things to pay attention to: the GPU is very critical for dense cloud and depth map generation. The CPU cores are really important for scale alignment and processing throughput. RAM is going to be your main bottleneck for speed and efficiency in really large data sets. So you're looking at a computer where 64 minimum gigabytes, and then storage speed, your NVMe, really impacts your workflow efficiency. So we do have 5 different packages that we actually put together for our customers. They range on the entry level from 3 to 7,000. Bear in mind, these include monitors, keyboards, mouse, everything. And you can see they're running on 32 or 64 gigabytes RAM. We have slightly ramped up in the 10,000 range, where now we're starting to get into the RTX 4090 graphics cards by NVIDIA. And then what we usually recommend, if people can swing it, is the Threadripper class systems, which are high throughput research grade computers. This is the AMD Threadripper Pro. And you can see the specs here, but that's going to be a workstation package around 15,000 when you put it together. So just to give you an idea of some of the computing requirements you need for really efficient 3D modeling. Now, like I said, I'm going to begin with focus stacking. We're going to be focusing on that B specimen. So the way the macropod is set up, we have our linear stack shot rail with a rotary stage on top of it with a dome that's now completely encompassing the specimen. The reason why there is no backdrop is because we can get a pure crisp black background because there's nothing for light to touch behind the specimen. And we mount that on a universal stage, which functions like a gimbal. We can rotate that specimen at any angle that we need within a 360-degree reference frame. And you can see where our flashes are located up here. That's what's giving us our illumination. So on the top of the table, we actually have a little white plate that'll actually white out the base as well, which is not pictured here. Focus stacking, if you are unaware, allows you to take several photographs through the specimen and then stitch together each individual focal plane until the final image is in focus. Again, Rick Littlefield is here to thank for making that possible. So this is a final image that's been completely focus stacked. To give you an idea of some of our optical capabilities today, obviously we can image anything that's really large. It gets really difficult once you start getting very small because of the wavelength of light. So this is a scale bar. It's a 5mm ruler imaged at 1 through 5x, and we're resolving 100 microns of detail. With the mid-to-Toyo long working distance objectives, we can resolve down to 2 to 4 microns in color. So this is that same ruler. Each machine groove is going to be 100 microns. So bear in mind, you can start to see light scatter at 100x. However, we can still resolve that information. So the image capture process is built by several workflows that we've now created in cooperation with several of our customers, actually. So this is the Big B macropod workflow. If you're curious about this project, you can go to bigb.net. This is where a big project and an NSF-funded project to digitize and 3D scan pollinating bees at many different institutions across the United States. But basically, every time you need to use the system, this is your guide or your workflow to set up your camera settings, your flash settings, your shutter, your step size for your depth of field, and so forth. So I just wanted to present this to show you it is pretty plug and play when you have the system going. So the first step of image capture is to balance your light. As I said, you don't want any glare. I realize that this image is out of focus. It's not necessarily to show you a final image. It's there to show you that we're setting up our light, we're making sure that there's no glare, and we have a very consistent uniform background, which is very important for 3D modeling. So we're setting this up using EOS utility by Canon for image capture. So we're taking several images at one perspective, and we're rotating the stage in 5-degree intervals, and we're repeating the process. Now in the end, wherever we set our directory, we get a big folder containing several images. So there are 41 times 360 divided by 5. So 360 degrees divided by 5 degrees of rotation times 41 individual focus stacks. And we need to separate these out every time a rotation occurred. So to make this really simple, we use an application called FolderAx. You can also write applications in R or code them yourself to just split this directory by the interval of images taken. So in this case, it's 41. And that's going to separate out all of our folders automatically into individual focal planes. So now we have that step done. The next step is to turn to Serene Stacker, where we want to batch process each of those folders. So in order to batch process, you open up your batch queue. You're going to drag all of those folders into your current batch icon or window. Oh, that just disappeared on me. And then on the right side, you're going to set up your alignment function, the folder you wish to save your final output images, and then of course your queued tasks are going to be shown below. And then you can process these, and in a period of time, they're going to start to focus stack, and the final output images, which are fully in focus, are going to be saved on the right. And you do not need to edit these photos, but you do have an option. My preferred method, of course, is to use Photoshop. If you use Photoshop, you can actually record the history of any edit that you do for one photo. Then you'll shut down the history, you'll save it, and then you'll reload it using an image processor. So it's just file scripts, image processor. And you're going to load the history that you just preserved, as well as select the folder where your images were captured, and it will apply bulk edits or batch edits to all of those images in one seamless move. Now the photogrammetry part begins. Masking is optional. Bear in mind that when this presentation was put together about 3 years ago, and Metashape has undergone several iterations of updates since then. I actually find that masking isn't necessarily critical today. However, there's two different ways to do masking. One is manual. You use a lasso tool, just like in Photoshop, to select the background and mask it out. Or you can create a single black image that matches the background and import it, and then apply a mask that way from your background, and then it takes the silhouette of whatever it is it's recognizing and forms a mask. Masks do help if you have a very complicated specimen, like something that's very hairy, or something that's very iridescent, in terms of isolating background and also creating a silhouette that can be picked up in a stereo visualization. The next step after you mask, and like I said, it's not required, but this step is absolutely required in the workflow, is to align your images. So each of those little pink frames is essentially where the camera was positioned around the specimen when a set of focus stacks was captured. And what we're able to visualize, is this alignment came together really well because we have a perfect sphere. We can deduce that those images are where our camera indeed was. And in the center, we can see that we have a point cloud that is roughly depicting the shape of our specimen that we want to visualize. So the next step is to then create a mesh from that low density point cloud. The old method is to create a high density point cloud. So basically, you want to create more points from the low density point cloud that you see. But there's a new method that's been created. We've been working with Agisoft quite closely, and they've created something called the depth map function, which uses stereo imagery. So essentially, this is basically taking that silhouette cutout that you see around the specimen, is creating almost a 3D stereo, and it is building a model using that type of a function. It's very fast, and it's also very good. So what I'm going to do now is, from using this mesh function, I'm going to show you a fast, low-quality build model, which is here. So this one probably took, at the time, probably 5 to 10 minutes. But of course, you can see it's very, it's not very refined. You can't see many of the hairs. You can't see a lot of the points. So if you do it in an ultra-fine model, which I think this one I'm about to show you isn't even ultra-fine, it's just high quality, we have a lot more detail within the bee. We can actually make out the eye, the antennae, the hairs, the abdomen, the structures on the abdomen, and the wings. Now, you do have editing capabilities to filter out these other areas which failed, where you can see holes in the wings when it gets to that. But I'll also say that 3 years of updates and iterations has really well sorted that, even without having to tweak and modify those settings. But if you do have holes, I just want to show that you can close those holes right within the toolkit of the software. So you can go to Tools, Mesh, close holes, you'll highlight an area, and you'll just close them using the surrounding data that the software is picking up on. The last step is to build textures. So now we want to take our color TIFF data or JPEG data and wrap the model with the actual images that we've captured. So now the last step of the workflow, I'm building my texture, and now my model is nearly complete. But like Duncan said, sometimes we want to actually take it a step further. So I'm going to export this model. We'll just save it as an OBJ with a straight JPEG mosaic to wrap the model. And we want to modify it using Blender. Now, Blender is free, off the shelf, very powerful, and very hard to learn. So I want to warn you, I'm just going to show you the first 10 steps. When you open the software, you're going to see this gray cube. First thing you could do is right-click and delete it. Now you want to import your model. So File, Import, Wavefront, OBJ. Believe it or not, I mean, if you're new to this, it's going to take you half an hour just to get to this step. So that's why I'm trying to show this. But now we're going to import this OBJ file, and we need to position this in the center and then begin editing. So if you see something that could be helpful is you can see that this is in object mode. You want to change that to edit mode, and that makes this entire model editable. So now we can actually edit the triangular mesh, and this is so powerful. You can actually get this looking perfect if you have enough time, and there are also automated functions in here, but I just wanted to bring it to everybody's attention that this is a good step in the workflow to know and have if you're doing this kind of work. After you fix those holes, you can then import it back as a .obj file, import your model, and then you can do things like add scale bars, do volumetric measurements. So we have our scale bar that we've overlaid according to the magnification of the lens we're at to a high degree of accuracy. And then we can either measure something like this with the width of the pin, or we can measure that scale that we have, or the entire length of the head, or anything that we know we have a fixed metric, and then we can add our scale bar to these models, which is really quite nice. Okay, so that's really the entire workflow of building a model. I hope that's informative for everybody that wants to do this and hasn't jumped into it. And now what I'd like to do is just talk about the same approach with a couple of different specimens. So very different. I'm not walking through the entire technical approach to these. I think you kind of got that from what I just gave. So what I'll do is I'll show this to talk a little bit about the specimen, and then you can see how the image was built by looking at the alignment in Metashape. So this is a large specimen, as I mentioned. It's about 25 centimeters long, and this is a rotation only. We don't need a focus stack because it's a large specimen. We can use a high f-stop to sort of achieve a greater depth of field. So for this, I built a large platform. You can see it depicted here. And this is positioned on the same rotary stage, but we've separated the camera from the stack shot in two different places, and they're at a greater distance. So now I can rotate my specimen, and I've got it lifted up on these mounts that we can build and plug and play to support that item. And that's how we would capture all of our data. So what you're looking at here, again, all those blue frames are spheres around the subject. Now, I probably did a bit overkill. I probably didn't need to take this many images, but again, with this many images without focus stacking, we're looking at a 25-minute top capture time. But I was also 3D printing this model, so I wanted it to be exceptionally accurate, which is why I did gather so much data. But you can see what we did is we moved the camera at different angles or pitches across the specimen in order to create, or at least attain, the data critical for building the 3D model. And in the end, this is what we're left with, a very, very accurate depiction of the specimen. The next specimen is something that's long, large, heavy, cylindrical. This combines focus stacking, panoramic imaging, and rotation. We're not as magnified, so our depth of fields are much longer. So as opposed to 41 individual focus stacks, we're taking on the order of 5 to 6 at an aperture of about f8. So here, again, our capture time is going to be significantly quicker, 30 to 45 minutes. And what we've done here is we have our core scan system, and we have our drill core mounted on top of our stage mount. And we can pan down core, take our focus stacks, and then here I actually did a manual rotation of the core, probably every 20 degrees. However, this will be an automated part within the next 2 months. We are going to have a roller that's going to automatically roll core, so that this will be an automated process as well. But it's really, really good to show this because it also demonstrates some of the capabilities of Metashape, where you do not need to capture the entire specimen in the field of view in order to do this. I did not have to render the panoramics before I processed this. I took image crops of the core sample, stacked just those crops, and then I imported all of that data into Metashape, and I was able to get a very, very accurate rendering of the 3D model. So again, those blue frames, each one of those little hash marks is going to show you where an image was captured. And here in the end is the model. We can actually enlarge this to full grain scale and look at submicron mineral grains in here. It's very detailed. The last one I want to show you is, it was a pretty exciting project. The United States Air Force and Space Force and SpaceX approached me and said, we have this project that's being launched on Polaris Dawn, and we can't get good 3D models of this without destroying the specimen while looking through the vessel. Can you give it a go? Put it on the system. Pretty quickly, we had a model, and in only 6-minute capture time. So here, these are on centimeter by centimeter plastic cleared cuvettes. They have to be plastic in space. They can't have glass. And this was just a great project to work on because it had so many different challenges associated with it. As you can see here, we can't use a round vessel because if it's round, it's going to introduce distortion. But also because it is planar, we also have the problem of a refractive index of the surface where the actual image is being shifted the same way a lens would shift what we're looking at. So we were very limited in the amount of data that we could capture. So we had to shift this cuvette in 3-degree intervals, but single exposures at an aperture of f12, because we don't need a really clear model, we just need the structure. And then as you can see on the image on the left, how we're sort of oblique, we're looking at it corner on, we just discarded that data. So as you look at this model construction, we've deleted the information where we captured the corners, and we tried to focus on our 3-degree angular rotation across about 18 to 21 degrees along each plane of the cuvette. And we were really surprised with the result. It was very accurate that we were getting. So because of this, when Polaris Dawn launched, they launched 16 specimens, 8 mutants, and 8 wild types. And we were at the launch site to 3D model those when they came back. And we have 3 publications in queue, so please stay tuned for those. That's been a pretty neat project. I'd like to just end on our YouTube channel. So I'll put a link in the description, but all of these videos and models that I walk through in greater detail, I've described on our YouTube channel from beginning to end. So if you do want to follow along and you're curious, feel welcome to subscribe to our YouTube channel and watch those there. And of course, I'd just like to thank everybody again for having me here today. I'd like to thank iDigBio, my fellow presenters, and everybody we've worked with over the last 10 years. Thank you.